Testing 1, 2. Morning, Kutso. Good morning, can you hear me? I cannot hear you.
Hallo.
Hallo.
Hallo, hoe gaan dit?
Baie lekker. Ek is baie impressed met jou graad 11 leerder sover.
Dit is baie goeie
Ek weet nie hoe
nuus.
dit ervaar nie, die klasse nie, maar dit lyk asof hy bietjie meer confidence begin kry, bietjie meer in het with it kom, as ek daai term kan gebruik.
Ja, nee, beslis. Al twee van hulle is baie beïndruk met hierdie lesse. Ek is so dankbaar vir jou.
Dis goed om te weet. Ek is so bietjie met Kutso kry ek die gevoel hy's so klein bietjie besig om vinnig vooruit te werk en ek voel nog nie dat hy in beheer is van die werk wat hy klaar gedoen het nie. Verstaan, as ek na die hoeveelheid vrae kyk, wat hy het elke week, dan voel ek hy skiep so vinnig oor die werk en hy gaan nie diep genoeg of doen dalk nie genoeg voorbeelde of staan nie lank genoeg stil op een plek tot hy dit verstaan nie. Maar dis 'n gevoel wat ek kry net op 1 of 2 of 3 keer wat ek met hom gesels het. So ek kan dalk verkeerd wees.
Okay, ons sal met hom praat en kyk. Soos wat ek sê, ek het my honeurs in wiskunde. Wiskunde verstaan ek, maar as ek kom by die wetenskap dan wil ek weghardloop.
Jy kan eintlik maklik reg kry.
Ek wag net vir Kutso, hy is op pad, hy het nou net aangekom. Kutso, come in. You can sit. There we go. En ek het lekker speakers gekry, so nou kan ons jou goed hoor.
Waar is julle nou weer?
Sekunda.
Sekunda, okay.
Ja.
Good morning, Kutso.
Good morning.
Okay, I just spoken to Liesel, and I told her that I'm just slightly worried that you're maybe working a bit fast or not, and not deep enough, not doing enough examples. Remember, you can also always go online and just type in grade 12 physical science past papers, and you'll get to the government site or Eastern Cape. You can do any of the CAPS, any of the government papers are CAPS based. So you can just draw some of those papers from the internet and then maybe just do the momentum and impulse sums in each of those papers, just to make sure that you are actually on par with what they want.
Oh, okay.
So I mean, for you to try and finish off the vertical projectile movement in 1 week it's quite fast. So I was looking at the examples you're sending me. You're sending me normal examples. You're sending me graphs. It means that you've actually tried to kill off that chapter in 1 week. That is actually moving slightly too fast. And I think it might be because you're working in one textbook that it's easy actually to complete all the questions in 1 week. But if you increase your workload a bit by adding other papers and stuff, then you'll find it will be harder to complete all the work in 1 week, and then it will force you to work slightly slower and do more examples.
Oh, okay.
So we can't be doing the graphs until we actually understand how the equations work and until we understand the basics of vertical projectile movement.
All right.
So what you can do, you can always just get me to do a lesson first before you attempt the chapter.
Okay then.
Okay. But at the moment, it's fine. Look at the chapter and then you have your questions. But we must try and find out a way that you work, you don't work too fast or too slow, but that you do enough examples. Your textbook doesn't have enough examples in. We'll have to. I can send you more examples, but you have internet, so you can actually just download them.
Yeah, okay, I will.
You don't even have to print it. You can just download it. And then you go and look into what each of the physics paper 1 has a momentum impulse question, and it's got a vertical projectile movement question. You can start doing those examples. If you really struggle, I can just send them to you. Also, okay. Let's start. I'm not gonna do those examples that you've asked me to do. I'm first gonna take 15 minutes to explain something, and then we're gonna go to those examples. But because I think the basics of this chapter you might be missing. I've written down 3 different equations of motion. Do you somehow have those equations of motions with you on a paper? Those are the standard ones. There's one more that I never use. It's final velocity plus initial velocity divided by 2 times the time is the displacement. That's the 4th equation.
Yeah, I know that one.
Okay, but you must know all 4 of them, or you must at least have a paper in front of you now with all 4 of them. It's like a formula sheet. Do you have a formula sheet?
I don't have a formula sheet.
Okay, you must get a formula sheet. You can take any paper, any physics paper from the internet. The last page is a formula sheet, and that formula sheet you will always get with every exam. It's not just one page, it's a couple of pages. But at the moment, what I want you to do is at least have these, take your textbook next to you, and you must have these 4 equations next to you so you can use them. Okay. Right. Now, there's 2 things that you have to understand very well, otherwise you can't do this chapter. The first thing, I'm going to draw a person here, and he's got a ball in his hand. Now what he's going to do, he's going to actually throw the ball upwards, and let's say at B, the ball is at its maximum height, and then the ball is going to fall down. I'm going to have a ball here at a random position called C, and then the ball is going to fall on the ground just before it lands on the ground. So we have A, B, C, and D. Now, when there's no air resistance or external forces acting on the ball, in other words, the guy is taking the ball and throws it in the air. The moment the ball leaves its hand, the ball is in what we call free fall. So the ball moves up into rest, falls down again, but there's no external forces. So there's no air friction. No external forces on the ball. Then the ball is in free fall. It's called free fall. And the acceleration of the ball is g, and that is 9.8 meters per second square downwards. So at any of those positions, doesn't matter where it is, A, B, C, or D, the acceleration of the ball is 9.8 meters per second downwards. So even at B, where the velocity of the ball is 0, where the ball is actually at its highest position, where it's standing still basically in midair, the acceleration of the ball is 9.8 meters per second downwards. So if you take a ball or any object and you throw it up in the air, the minute it leaves your hand, the acceleration is downwards, and we call it g, 9.8 meters per second square. That is x, very important. So even if you throw the ball up in the air, it accelerates downwards. That is like basic, a basic concept that you have to understand. This is the first one. And then the second one, okay, let's say I've got a object, like a building or something, and I'm throwing a ball from the building's edge upwards. So there the ball goes up, and it falls on the ground there. Okay, so we have A again, where it leaves my hand, B when it's maximum height, C is when it hits the ground. Okay, right, so the displacement of the ball, let's say this is a 100-meter building. The displacement of the ball at A equals 100 meters downwards. So even if you stand on a 2-meter high roof and you throw a ball up in the air, another 10 meters in the air, and the ball falls on the ground, the displacement of the ball, delta x, is 2 meters downwards. It doesn't matter how high you throw it up in the air, the ball only displaced 2 meters downwards. Do you remember that from grade 10, where we worked with distance and displacement?
Yeah, sort of.
Okay, so there's boy again. He's got a ball in his hand. He throws the ball upwards 4 meters, and the ball comes down and it lands in his hand again. What is this displacement of the ball?
When he throws it 4 meters upwards.
He throws the ball up 4 meters upwards. In other words, the ball comes down another 4 meters. What would you say is the displacement? What is delta x, the displacement of the ball?
4 meters.
0 meters.
Okay.
The distance is 8 meters. The ball traveled 8 meters, but the displacement is 0. Remember, displacement is a straight line from its starting position to its end position. In this case, on the left, 100 meters. In this case, the ball starts here, it ends here. There's no distance between the starting and ending point. The displacement is 0 meters. If you understand these two concepts, then suddenly this projectile movement chapter becomes really easy, or well, moderately easy. Okay. So, here's another man, and he's running towards Stop Street. It is 20 meters to the Stop Street. He runs to the Stop Street. What is his displacement? 20 meters east. Now, then he runs back another 20 meters. What is his total displacement now? 0 meters. He ran 20 meters to the Stop Street. He ran back to his original position. There's no distance between his starting point or his initial position and his final position. So his displacement is 0. Okay, let's do example. Make up our own example. There's a roof or a building again. It is 80 meters high. There's a ball or object. The object is thrown upwards at 2 meters per second. Let me just get that right. This doesn't look nice. So we're throwing the ball upwards at 2 meters per second. Goes up. Bang, it falls on the ground. Right. Now there's various questions they can ask you. The first question might be, what is the velocity at which it hits the ground? That's one type of question they can ask. So what's the velocity here when it hits the ground? Okay. First thing you can ask yourself, what value don't we have? If you look at those equations of motions next to you, you have initial velocity, final velocity, you have displacement, you have acceleration, and you have time. One of those values we don't have. Which one's that? Okay, let's see. There's initial velocity, there's final velocity, there's time, there's acceleration, and there's displacement. Let's fill in all those values. Okay, what is the initial velocity. Right? Before we answer that question, let's choose the downward movement as positive. That's a very important choice to make. You can either choose upward as positive or downward. I normally choose downward movement as positive. And there's a simple reason for that. Because then your G value, your acceleration is positive. 9.8 meters per second square is positive. If you don't choose downwards positive, you always have to use a negative G value. And that you sometimes forget, and then you stuff up the whole sum. So I'm doing downwards as possible. That means my initial velocity is negative 2 meters per second. The final velocity is what I want. Time, I don't have. And can you tell me what the displacement is? It's a positive 80 meters because it's downwards. The displacement is the distance between its starting position and its end position. And that's 80 meters. So now you have to find an equation that does not have time in it. And this is this one. The final velocity square equals initial square plus 2g delta x. Is that correct?
2G, that's nice.
Can you hear me, good sir?
Yeah, I can hear you.
Is that the equation that doesn't have time in it?
Yes, it is. I
So
can
that's
see
the
it there.
easiest one to use because we don't have a time value. We don't have it. Okay.
Yeah.
Cool. So final velocity is, I don't know, initial is negative 2 squared plus 2 times 9.8 times 80. And that's just calculator work. Tell me what calculator do you have?
Casio.
What's the code on it?
Hold on. Mm,
Is it a FX what?
it's an FX.
Yeah, FX what? Is it a
82.
okay? 82
It's an
FX something.
A2VA plus.
Okay. All right, cool.
Yeah, something like that.
Do you get 39.65 meters per square downwards?
Let me just
Check that, double check that.
Okay. Yeah, I do get it. 39.65 meters per second. Yeah.
Yeah. Was there another way of doing it? Sure. You could have worked out the distance from it where I launched the projectile until it reaches its highest point. And then you can make a new sum starting at its highest point down to the bottom there. And then you've just added the new distance to the 80 meters. You do two sums. But that's a waste of time. Cool. Okay.
Yeah.
You can take a screenshot of that because I'm going to delete it and ask a new question of the same sum.
Just gonna call my teacher.
You can write it down as well, or you can just take a screenshot. It's up to you.
I wrote down everything already.
Yeah, you can write it down. So I mean, I'm teaching you how to use these equations now.
I already have everything down.
Okay, can I delete this?
Yeah.
Okay, let's ask a new question. We don't have any values. I'm just going to make this very small. Assuming we don't have any values. Whoa. Just going to try again. Let's assume this was not the question. They could have asked also, one, how long does it take for the ball to hit the ground? How long does it take? How long does that movement take? Right, so I have initial velocity. It's -2. Final velocity, I don't have, assuming we haven't done the first part, so I don't have it. Time is what's asked. G is 9,8. Displacement is 80 meters. Positive. Right. Which equation does not have final velocity in, but has time in? It must have time in because time is what we want to calculate.
And that's what you're trying. I see.
It's the delta X one.
Still trying to find it.
You must have that page next to you so you can look. There's only 4 equations that you have to browse over. And this is the one that doesn't have the final velocity in. Why? We don't have it because we're assuming that this is a new question. They haven't asked anything else yet.
Okay.
I'm going to show you a couple of ways to do this. One other method, basically. Cool. Now what? The displacement is 80. The initial is -2t for time, plus a half times 9,8 t squared. You know exactly what I'm doing now. I'm just filling in the values. So I have 80 equals -2 plus 4,9 t squared. So I have a quadratic equation, 4,9 t squared minus 2t minus 80 is 0. And then you're going to use that formula. That's why I asked what calculator do you have. If you had a FX991, then in science, you don't have to write this formula. You have to now do this. Minus b plus minus root of b squared minus 4ac over 2a. Now in science, you don't have to write that. You can just write the answer. So with a silver calculator, you just don't even do that quadratic equation. You just pop in the values, it gives you the answer. Okay, so you understand what I'm doing now?
Yeah.
Hmm?
Yeah.
Good. So it's -2 plus minus -2 squared minus 4 times a times c over 2a. Right. You can write that down. I'll give you the answers because I'm cheating on my calculator. So the time is 2,4. No, sorry. It's 4,25 seconds or -3,84. So this is not applicable. Can't have negative answer. Therefore, the time is 4,25 seconds. Takes 4,25 seconds to hit the ground. Tell me when you're ready.
Now I'm ready.
Okay, cool. What else could you have done? Just talk to me. What other method could you have done to answer the same question, you think? You could have worked out the time it takes to get its maximum height. Let's say it was 0,2 seconds. Then it will take another 0,2 seconds to go down there. And then you can just work out that B to C time. But that's harder because there's more calculations. So let's look at your questions. The first one, where is this now? Okay, Morno throws a cricket ball vertically up in the air. So I'm assuming he's standing on the ground, is he? So there's the guy. They call him Morne. He takes a cricket ball and he throws it vertically up in the air at 20 meters per second. The ball falls back into his hand. What is the maximum height? What is the maximum height of the ball? Do you know how to do that? Right, the first thing we're going to do is choose direction as positive. We choose downward as a positive direction. Okay, then we ask, what do we want? We want to know the displacement of the ball upwards. Okay, that's what we want to know. What other values do we have? We have an initial velocity of -20. Is that correct? Because we're throwing it upwards. If it reaches its maximum height, no? Is this a question you had, good sir? Just want to make sure. Yes.
This is from the next topic. This is from the next topic, projectile motion. But yes, it is a question.
Okay. So we can work through this example.
Yes.
Is that right?
Yeah.
Okay. So the final velocity, what would the velocity of the ball be when it reaches its maximum height? I'm taking a ball and I'm throwing it upwards. Boom, 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 boom. And there it reaches its maximum height. And then it falls back. At its maximum height, the velocity will be 0. It will be standing still in the air. It will stop. So in other words, if you throw a ball up in the air, some other time it will slow down until it starts slowing down immediately when you throw it. But some other time it will reach its maximum height and then its velocity will be 0. So the final velocity is 0. The time it takes, I don't have. But the acceleration due to gravity is 9,8. So I'm looking for an equation that doesn't have time in it. Which one is that?
It's the
Vf square equals Vi square plus 2g delta x. So I have 0 is -20 squared plus 2. Now, very important. G, which is 9,8, delta x. Cool, do that. 400. Do that and tell me what answer do you get. Delta x is do you get -20,41? It's 408 actually. Come Kutsu, calculator.
Yeah, no, I don't get that.
No. Okay. Right. So we have 0 equals -20 square is 400 plus 2 times 9,8 delta x. I throw the 400 over, it becomes -400. And that is 2 times 9,8 delta x. I divide the -400 with 2 times 9,8 to get delta x.
Okay, I can see the mistake I made.
Okay, just check that. You knew actually that you had to get a negative answer because the movement upwards is negative. The displacement upwards is negative. So I need to get a negative answer. So that is 20,41 meters upwards. They use delta y. I'll show you now why they do that. Delta x is fine. You can use either one. Can I go on?
I'm almost done here. Yeah, you can go on.
Okay. In the past we had vertical and horizontal projectile movement. So to distinguish between the two, we use this one as delta x because it's like on the x-axis, and this one is delta y because it's on the y-axis. So you'll find in the memo they might be using delta y, but no stress. The equation is actually delta x. So we usually continue using delta x. Okay, for next question. The time it takes for the ball to reach his hand again. Right, speak to me. Very important. There's the guy again. He takes a ball. He throws it up in the air. It falls down back in his hand. The upward velocity is negative 20 meters per second. Right, I want to know how much time does it take to be back in his hand? There's two ways of doing it. You can either calculate the time it takes to go up and multiply that with 2. Because there's no friction or external forces, the time it takes for the ball to go up in the air is exactly the same as the time it will come down. In real life, that is never the truth. If you hit a ball, take a tennis racket and hit a ball in the air, and it leaves the racket at a certain velocity, it won't come back at that exact velocity. It will also take less time to go up and more time to come down. But anyway, that is not what we're going to worry about because we have perfect conditions here. So what are we going to do? Let's get all the values we have. We have the initial velocity, that is negative 20 meters per second. We don't have the final velocity. In other words, the velocity that it hits your hand. Or do we? No. We want to know what the time is. We have G, which is 9,8 positive because it's downwards. And we have the displacement. It's 0. I'm looking for an equation that doesn't have a final velocity in, and that is the delta x one, vi delta t plus half g delta t squared. Right, this time my displacement is 0. Remember, if you throw it up in the air, it doesn't matter how high it goes. If you catch it back in the same position, your displacement is 0. So the initial velocity is negative 20t plus a half times 9,8 t squared. So I have 0 equals negative 20t plus 4,9 t squared. And that you can just factorize if you want to. You can solve it with a quadratic equation. T can't be 0, so you can even divide with t. So I'm just going to do this. 0 equals, I'm going to factorize out t. Then I have negative 20 plus 4,9 t. So t can't be 0 because 0 is the time that it leaves your hand. Therefore, minus 20 equals, okay, let's do it, minus 4,9 t. I just did this in my head. There's other ways of doing it. You could have just said 4,9 t must be a positive 20 because negative 20 plus positive 20 is 0. And then I'm just dividing 20 with 4,9. Then I get 4,08 seconds. It sounds way too much. Okay, throwing it at negative 20 meters per second upwards. That is super fast, actually. They have the answer. They did it differently. Oh, they chose showed you two methods of doing it. This is the method we chose. Okay, we're going to do that displacement time graph now. Remember what they've done. Just take down my notes. I'm going to show you something different to what we've done.
Okay.
Are you ready, Kutsu?
Yeah.
They've just done something different on the memo. That they have chosen upward as positive and downward as negative. So they've used negative 9,8 the whole time. I don't like that. It's something you forget. And once if you forget that, to put that value as negative, you won't find you won't realize in the answer. You won't know that you've chosen it wrong. Okay, now they want a position time graph. Okay, so their way of drawing that position time graph is very easy. We're going to struggle slightly more. We have chosen downward as positive, so our graph is slightly harder. So I'm going to draw a system of axes here with my horizontal and vertical axis. So now your x-axis, which is time, that becomes your point of reference. So in other words, you can, okay, this is not a difficult example. Let's assume that you are an insect or something sitting on the person's hand next to the ball just before he throws it. Then the ball's going to be next to you. So there we start with our graph. And then the ball goes upwards. So you, that small insect, and you're looking at the ball while the guy is throwing it upwards. So the ball is going away from you in upwards position, and upwards is negative. So the graph would look like this. You'll be referencing his hand. So with reference to his hand, the ball is going up, further away from you, and up is negative. And the maximum height we worked out as 20,41, negative 20,41. And the total time it takes to hit the ground was something like 4,05 seconds, or 8 seconds, 4,08 seconds. We didn't work out the time it takes, but this will be half of that, 2,04. So there's your graph. Our graph is slightly harder to draw because we have chosen downwards as positive. They've chosen upward as positive. So they just follow the curve as it's thrown. But I teach the student to do the following. I say, look, forget about the graph. Just do the following. Just draw on a system of axes what the ball is doing. And they say, okay, the ball starts here. It's thrown upwards. Bang. And it comes back. Okay. This is the drawing if you've worked on upwards as positive. But we worked on downwards as positive. So what they do with this graph, they just flip it over to the other side. No, this one doesn't flip over. So in other words, they draw a pencil graph like that, and then just go pen, and they flip it over to the other side, and then they delete the other one. We're going to do a lot of these graphs. And the ball is also going to start bouncing. So this is correct. Okay, next one. There's a person that stands on top of a 40-meter high building. There's the building. It is 40 meters high. He leans over the edge and throws a stone vertically upwards. So he throws a stone upwards. There's the movement of the stone. And it's upwards thrown at 12 meters per second. The stone lands on the ground next to the building. There, boom. Okay, what do we have? We have the initial velocity, and we're choosing downwards as positive. So the initial velocity is negative 12. We have the displacement. The displacement of the stone is 40 meters downwards. We have G, that is 9,8 meters per second square downwards. You don't have to put those units in. You can just get the values. There's no marks for writing it down. This is just to help you. What else do we want? We want to know what is the time it takes for the stone. What's the time to reach the ground? So how long does it take for the stone to hit the ground? Okay. So Kutso, you need to find an equation that we can use. Which one?
We don't have final velocity, so we would have to use the change in x is equals to the VI time, or changing time plus the half gravity changing time squared.
Yes. That's just shorthand called the displacement formula, because it starts with displacement. Okay, cool. What's the problem with this formula? There's a small problem with it. And it's a quadratic equation that you have to sort out. Okay, but you can do that, so it's not a problem. So the displacement is 40. The initial velocity is negative 12 times t plus a half times g, which is 9,8 t squared. So I have 40 equals negative 12t plus 4,9 t squared. Everything to the right. And then you see, I have a cool calculator. I just do this, and then I go mode equation, and I tell the calculator what the A value is, 4,9. I tell the calculator what the B value is, it's negative 12. I tell the calculator what the C value is, it's negative 40. And then it basically solves the equation for me. I get 4,33 seconds. The other value is negative 1,88 seconds. So I just leave it like that. Now in science, you're allowed to do this. This is full marks. You don't have to show, like in maths, how you get those values. But if you don't have that calculator, then you follow the blue route. You go t equals minus b plus minus b squared minus 4ac over 2a. And then you say t equals, and then you can just put the values in and get the answer. But I'm not going to waste time. You know how to do this, eh? Is that correct?
Yes.
Good. Next question. The maximum height from the ground that the stone reaches. Okay. So what is the maximum height from the ground? Well, I need to only calculate the maximum height that it traveled and add 40 to that. So the only thing I have to do, I have to just work out what is the displacement of this first section from where it's pitched at negative 12 meters per second, where it reaches its highest point at B, where its velocity is 0. All I want to know is what is that delta x value, because then I can just add it to 40. Is that correct? Yes.
Yes.
So in this little section, I have an initial velocity of negative 12. I have a final velocity of 0. I have a gravitational acceleration of 9,8. And that's it. I don't have time. I want to know what displacement is, but no time. And then I use this again. Vf square equals Vi square plus 2g delta x. And this time I'm going to figure out what delta x is. So when it reaches its maximum height, the velocity is 0. The start velocity is negative 12 squared plus 2 times 9,8 delta x. So that's quite easy. That is 12 squared divided by 2 times 9,8. Then you should have a negative sign in somewhere because I'm throwing those values over to the other end. So that's 7,346. Upwards. No, I don't have to give any units there or answers. Why? I've just worked out from the tip of the building upwards. So therefore the height from the ground is 40 plus 7,346. And now I'm rounding off to 47,35 meters. Did they work this out? That wasn't a question, was it? I don't know. Oh, that's probably on a different memo page. I don't have that memo. Well, that's the question. What is the maximum height from the ground? I've just worked out what's the height it displaces. And so I just added that to the 40. Are you happy today, Kutsu?
Yeah. Yeah, very.
You're understanding slightly more.
Yeah, actually very much.
Good. Okay, now we have problem sums. The balloon in the air is a problem sum. Okay, let's draw a little picture. There's my balloon. The hot air balloon rises at a constant velocity of 5 meters per second. So we're standing in this balloon and it's constantly rising at 5 meters per second. There's a guy with the name of Abraham. Okay, he's in the balloon. He leans over the edge and takes a photo with his camera. Okay, and obviously the camera is going to fall. Now, while he's doing that, he's 200 meters above the ground. He drops his camera, which is a bad idea. Okay, so let's just make that camera red. There's his camera, and the camera drops off the edge. Okay, what's the acceleration and the initial velocity of the camera respective to the moment it's dropped? Okay, I want to know two things. What is the initial velocity of the camera? So, what is the velocity of the camera when Abrams got it in his hand? You're hanging over the balloon with the camera in your hand. You're taking pictures down. What is the velocity of the camera? The camera is moving at 5 meters per second upwards relative to the ground. Relative to the balloon, the velocity is 0 because the camera and the balloon is moving at the same velocity. But relative to the ground, the camera is moving upwards. Imagine you standing on a very high mountain and there's the balloon coming. It's moving upwards. And you're sitting here on this mountain. And now you see Abraham in the balloon with a camera in his hand. And this balloon, basically, with the camera, is moving upwards past you. Then relative to you who are sitting on the ground or on the mountain, that camera is moving upwards at 5 meters per second. Okay, you understand that? Okay, what's the acceleration of the camera? Okay, now we must just make sure, when are they asking that? When acceleration? So let's ask, what is the acceleration of, okay, that G is not a good term to use. Let's just write acceleration. What is the acceleration of the camera? What is acceleration and initial velocity of the camera respectively to the moment it's dropped? Respectively at the moment it's dropped. Okay. Okay. At the moment it's dropped. The moment it leaves Abraham's hand, the acceleration of the camera is 9.8 meters per second square downwards. A stands for acceleration. So the moment you drop that camera, while Abraham had it in his hand, the acceleration was 0 because he was moving upwards at a constant velocity of 5 meters per second. But the moment he leaves the camera is in free fall, and that means the camera is moving or accelerating towards the Earth at 9.8 meters per second. Calculate the total time it takes for a camera to reach the ground. That's very easy now. What's happening here now? I'm just going to make this smaller, this question. Right. How long does it take for the camera to hit the ground? Let's do that. How long for the cam to hit the ground? What do we have? We have G as positive 9.8 because we're choosing downwards as positive. We have the displacement as 200 meters downwards, so it's positive. We have initial velocity of what? That is tricky. What is the initial velocity? Okay, we said it's 5 upwards, so that's negative 5 meters per second. Remember, if he leaves the camera is traveling at in 5 meters per second upwards. So that sign is very important. The final velocity we don't have, and we want to know what the time is. We're looking for an equation that doesn't have final velocity in it. Again, it's the displacement equation. And we're going to do some quadratic equation again. So the initial velocity, negative 5t, displacement is 200, plus half 9.8 t squared. So 0 is 4.9 t squared minus 5t minus 200. Okay, you're gonna write that, get the stuff in your calculator, see if you can work it out. Calculate it. You calculate that and see if you can get the 6.92 second answer.
Yeah, I got the answer.
Very good.
6.90.
You understand, we're using these two of those 4 equations you're going to use a lot.
Yeah.
Okay. What's the distance between the camera and Abraham's hand after 3 seconds after it was dropped? Okay, you've got these values now, don't you? So I can actually just delete them. Otherwise, I'm struggling for some space here. I should have made this smaller. There we go. Now I have more space. Okay, so after 3 seconds, okay, what is the distance between Abram's hand and the camera? Okay, so let's look at this little picture here. There's Abram's hand. Oh, let's just try a better hand than that. There's Abram's hand. He's moving upwards at 5 meters per second. There's the camera. The camera is falling downwards, accelerating at 9.8 meters per second. So I want to know, how far did Abram go up in 3 seconds, and how far did the camera fall in 3 seconds? And then I can just take that distance between. If Abram moved up another 20 meters and the camera fell another 50 meters, then the distance between the hand and the camera will be 70 meters. That's correct. So let's do the easy part first, and that is Abram's hand. So Abram's hand. We want to know what the displacement is. We have initial velocity of -5. We have acceleration. Listen, very careful. I'm just going to make it A. Abram is moving at a constant velocity. His acceleration is 0. And we have time as 3 seconds. If you're moving at a constant velocity, then you don't have any acceleration. So we can just use this formula. Delta x is vi delta t plus a half g delta t squared, where the displacement is the initial velocity times the time plus 0, because there is no g. Abram's hand is not in free fall because Abram is stuck to the balloon that is moving up at 5 meters per second. So that is just -15 meters, or you can say 15 meters upwards. And then we're going to work with the camera. We want to know what's the displacement of the camera, downwards in other words. The initial velocity of the camera is -5. The camera, just before it falls, or at the moment it falls, its upwards velocity is 5 meters per second. We don't have the final velocity. We have time as 3 seconds. And we have G as 9.8. The camera is in free fall, so that one has a acceleration of 9.8 meters per second downwards. So we can also use this formula. Initial -5 times 3 plus half 9.8 3 square. Right, do that. -15 plus 0.5, 9.8 times 9. And that's 59.1 meters downwards. So that one's upwards, that one's down. Okay, you're not allowed to do those arrows I'm doing. Okay. Okay, so I'm cheating. So that is good. I don't have to have values. I don't have to have direction there. It's not the question. So I can use -15 meters if I want to, or I can use 15 meters upwards. I won't be penalized. I will only be penalized at the end. So now I'm going to say that is like 74 meters, 74.1 meters. Eh? Do you agree? Therefore, the distance is the sum of those two. 15 meters up and 59.1 down. So the distance between that is 74.1 meters. I wish we had the memo for that. I probably have, but I didn't paste it. Do they have a memo of that? There's the balloon sum. 6,92 seconds. Did we get that? Yeah. Okay, they get...
Yeah.
Why do they get negative 29?
Oh, I can see now. Maybe you made a mistake there.
Okay.
Oh, 29.
Yeah, please help me. Retype it if I've made a mistake.
It's negative 5
Negative
times
5
3.
times...
Yeah, your
Did I make typing?
plus a half. No, I think you maybe saw it.
Oh, I made a
instead of
mistake.
2.
I didn't type that negative in.
Yeah.
Very good. Well spotted. There's a mistake there. So that is 29,1. It's still negative. No, it's positive. 29,1 meters downwards. Cool. So now the distance is 15 plus 29,1. And what's that? 44,1. No? And you don't give direction for distance. Distance is just distance. Distance is a scalar, not a vector. See if we can squeeze in another question. Okay, we're not going to do the graphs. We're going to do that later. We first have to get the sums right. Okay, there's a graph now. Okay, let's find something with another graph. What's this? Oh, the rest are all graphs. So what I'm going to do, so you're going to get some more examples from the internet in papers, and we're going to leave the graphs for next week. Okay. Because we're going to use the graphs. These graphs we use for vertical projectile movement, and we use it in momentum impulse sums. So the graph can be used for both. I want to go back to momentum impulse with the new knowledge we've got with free fall, and then we're going to do sums with momentum and impulse mixed with vertical projectile movement, and then the graphs. We will do the graphs of both of them. Because at the moment, your graph basically is just one-dimensional in the sense that we have a building there, we take a ball, we throw it in the air, the ball lands on the ground. So now you have a velocity time graph, something like, let's say, negative 5 meters is thrown up, it hits the ground at, let's say, 20 meters per second. So now your graph just looks like that. A is where it leaves his hand at negative 5. B is where its velocity is 0. So this is a velocity in meters per second time graph in seconds. So B is where the ball is at its maximum height, or where its velocity is 0. And then C is when it hits the ground at 20 meters per second. But if this ball now suddenly bounces, it bounces up again and falls on the ground again, then this graph will have another leg. We'll have a certain time it will be in contact with the ground, and then there will be another leg, another piece of the graph, and that piece is where this movement happens there to there. So this will be like E and D. D is where it leaves the ground, E is where it's maximum height again. And so the ball bounces. So, and then this little section here is momentum and impulse again, because the ball is in contact with the ground. There's a certain force on the ball, blah, blah, blah. So these two chapters are going to merge into one. And I don't really want to do the graphs until we can do both, the sums of both of them, because then otherwise you'll struggle with the graphs. Okay. Do you know where to find extra work online?
Ek weet waar.
Cool. Lekker dag. Ek wil julle nog weer, ek wil eintlik hê ons moet saam met daai ander kinders klas loop. Dit maak meer sin vir my. Maar voor ons nie 'n tyd kan kry nie, sal ons maar net so aanploeter. Julle wil obviously alleen klas hê. Dit is baie beter, né?
Ja,
Okay. Right. Ons gesels weer. Bye bye. Baie goed so.
Bye.
dit